Hello, Chem 111. This video is going to briefly talk about the Planck-Einstein relation, both what it is and how to use it. Okay, so I have the equation shown here in the red box, and the equation relates the energy of one photon of light to the frequency of that wave, the wavelength of the wave, the speed of light, and a constant called Planck's constant. Okay. And so it can be represented in two ways. One is using just frequency and Planck's constant, or using the speed of light and the wavelength. Okay, so I just want to define all of the variables here to make sure we're all on the same page. So energy is given by the symbol E, and it's measured in units of joules that have the symbol J. Okay. H, as I said a second ago, is a constant called Planck's constant, and it comes up a lot in chemistry. And it has the value of 6.626 times 10 to the minus 34th and units of joules seconds. Okay. And you can either write JS for joules seconds, or your book writes J.S. Okay. Nu is the symbol, let's see, so nu, it's pronounced nu. It is the symbol for frequency. Okay, in units of 1/seconds, or more simply, seconds to the minus 1. All right, so the notation S to the minus 1 means 1/seconds. Okay, and frequency is really the number of waves passing by a point for every 1 second. Okay, C is the speed of light, and that is also a constant. Okay, which is equal to 2.998 times 10 to the 8th meters per second, or more simply, meters seconds to the minus 1. Okay. And then finally, lambda is wavelength. Okay. And it is measured in meters. So anytime you use this equation, you need to make sure your wavelength is in meters. All right, let's look at a sample problem as a way to demonstrate how we use this equation. So green laser pointers, which I really love to use, emit light with a wavelength of about 532 nanometers, okay? And I want you to use the Planck-Einstein equation to calculate the energy of one photon having this wavelength. All right, before we jump into solving this problem, I want to talk about an important point here. I've given you the wavelength lambda. Whoops, that was my eraser. The wavelength lambda in nanometers, okay? But we want lambda to be in units of meters to solve this problem. So we need to convert 532 nanometers into meters, okay? So it's important to know that nano, or the N before the M, is equal to 10 to the minus 9th meters. All right, so nanometers is equal to 10 to the minus 9th meters. Okay, I'll just leave it as M. And we can convert nanometers into meters in a couple of ways. So you can either say 532 nanometers and simply replace 10 to the minus 9th for the nanometer units. So for example, we would have 532 times 10 to the minus 9th meters. Or we can do the unit conversion and say 532 nanometers times 10 to the minus 9th meters for every 1 nanometer gets us to 5.32 times 10 to the minus 7th meters in scientific notation. All right, I'm just going to erase this last line here and rewrite the equation so we can actually solve the problem. Okay, so we have energy is equal to hc over lambda. So if we put in our numbers here, we have 6.626 times 10 to the minus 34th joules seconds. Okay, and I strongly encourage you to include units here just to make sure that you've done everything correctly and end up with the right joules at the end of your problem. Okay, we're going to multiply Planck's constant by the speed of light, 2.998 times 10 to the 8th meters per second. Okay, all of that divided by the wavelength, or 532 times 10 to the minus 9th meters. All right, so if we look at our units, seconds is going to cancel out per second. Meters and meters cancel out, leaving us with just units of joules, which is exactly what we want for an energy. And if we plug this into our calculator, we get 3.732 times 10 to the minus 19th joules, right, as the final answer. So again, this is the energy of a single photon of light having the wavelength 532 nanometers. All right, here's a second example that asks you to calculate the wavelength of a photon with energy equal to 4.071 times 10 to the minus 19th. And I suggest that you turn off the video, see if you can do this on your own, and then you can watch me solve the problem. All right, so we can go back to our Planck-Einstein relation. Okay, so I've given you energy. Oops, so we know this. We know H and we know C. We want to solve for lambda, okay? And I really encourage you to rearrange the variables and solve for lambda using the equation rather than putting in the numbers and then rearranging. I think it's easy to lose exponents and mix up numbers if you try to do it that way. Okay, so I'm going to go ahead and multiply both sides by lambda to try to solve for lambda. So we've got lambda times E is equal to HC. And then if we divide both sides by E, we've rearranged to solve for lambda. Okay, so now we can go ahead and put in our known variables. So lambda is equal to Planck's constant, which is 6.626 times 10 to the minus 34th joules seconds, multiplied by the speed of light, which again is 2.998 times 10 to the 8th meters per second. And then we're going to divide that by 4.071 times 10 to the minus 19th joules. All right, so let's just cross out the variables that cancel each other out here. So joules and joules cross out. Seconds and seconds again cross out. So we're left with meters, which is exactly the unit we want. So we're good there. And if we plug this into our calculator, we should get lambda is equal to 4.879 times 10 to the minus 7th meters. Okay. And if we want to convert that to nanometers, we can say there are 10 to the minus 9th, or 1 nanometer is equal to 10 to the minus 9th meters. So lambda is equal to 487.9 nanometers. So a photon with energy equal to 4.07 times 10 to the minus 19th has a wavelength of about 487.9 nanometers.